Hello and hi everyone, my name is Muhammad Zuhilmi Imam bin Zakaria, and today I'm going to talk about the application of vectors in navigation. Let's start with the basics. What exactly is a vector? Vector is a quantity that has both magnitude and direction. This makes it different from a scalar which only has magnitude. Common examples of vectors include velocity, which describes how fast something moves and in what direction, as well as force and displacement. So, why are vectors important in navigation? Whether you are flying a plane, sailing a ship, or even sending a satellite into orbit, knowing the exact direction and speed is essential. Vectors allow us to calculate this precisely, making sure we stay on the right path despite external influence like wind or ocean currents. By the end of this presentation, you will understand three key things: the mathematical background of vectors, how to perform practical calculation with vectors, and how to apply this knowledge to the real world scenario. Now, let's explore the role of vectors in navigation. When an aircraft or a ship moves, it is rarely a straightforward journey. There are external forces at play, such as wind, ocean current, or even the rotation of the Earth, that can push the vehicle off course. Vectors help us break down this force into smaller, more manageable components, allowing navigators to calculate the actual path taken. For example, imagine a plane that intends to fly direct north. If a strong wind blows from the west, the plane won't end up going straight north. Instead, the wind pushes it slightly to the east. The plane's engine generates one vector and the wind creates another. When these two forces combine, they form a resultant vector, representing the plane's actual movement. This analysis helps pilots and captains adjust their heading to stay on track, ensuring they reach their destination efficiently and safely. Okay, let's dive deeper into an essential concept: vectors component. A vector is not just one single movement. It can be broken down into horizontal and vertical components using trigonometry. This is particularly useful when dealing with diagonal movement or forces coming from different directions. For example, let's say a ship sails northeast at a speed of 20 knots. At the same time, a 5-knot crosswind blows from the west. Instead of guessing where the ship will end up, we can split both the ship's movement and the wind into their horizontal and vertical components. By calculating each part separately using sine and cosine function, we can determine the ship's true path. This method helps navigators accurately correct their course, ensuring they don't drift off target due to unexpected force. Okay, next, I will explain the real-life application of vectors. Captain Aiman's flight to Langkawi. Captain Aiman, an experienced pilot, is operating a small aircraft from Kuala Lumpur to Langkawi. His plane route covers a direct distance of 410 km on 320-degree bearing from Kuala Lumpur International Airport, KLIA. However, a weather update reveals a strong 60 km per hour crosswind blowing from the west. Captain Aiman must now calculate his new heading to counter the wind and stay on course. Okay, let's see to the step 1. The step 1, we need to define the non-vectors, the plane's intended velocity, VP has a magnitude of 300 km per hour at a bearing of 3 to 0 degree. The wind velocity blows from the west with a magnitude of 60 km per hour. Okay, let's convert this into component form for easier calculation. For the plane's velocity, VP equal 300 cos 3 to 0 degree sin 3 to 0 degree. Okay, next we using the trigonometry. Cos 3 to 0 degree equal to 0.766 and sin 3 to 0 degree equal to negative 0.643, and we got VP equal 3000.766 and negative 0.643 equal to 229.8 and negative 192 192.9 km per hour. For the wind velocity, W equal 60 km per hour. Okay, let's do the step 2. The step 2, we need to calculate the resultant velocity. The resultant velocity combines the plane's velocity and the wind's influence. Okay, here is the formula. R equal to VP plus W. Okay, R equal to 229.8 negative 1992.6 plus with 60 and we got 289.8 and negative 192.9 km per hour. Okay, for the step 3, we need to determine the new bearing. Okay, next let's calculate the plane's new bearing. Okay, we calculate the plane's new bearing, we need to theta equal to arctangent negative 192.9 divided by 289.8 and theta equal to arctangent negative 0.9957 and theta we got negative 33.8. and since the resultant vectors lies in the fourth quadrant, east to north, the bearing is 360 degree minus 33.8 degree. We got equal 3 to 6.2 degree. Therefore, Captain Aiman is now aware that the wind diverts him to 3 to 9.2 degree. Yet he must maintain a course of 3 to 0 degree. Okay, next to the step 4, we need to calculate the correct heading to counter the wind. Captain Aiman must adjust his heading. Okay, here is the formula. VP equal to R minus W. Okay, R is 229.8 and R is 229.8 and negative 192.9 and W is 60 and we substitute the value into insert the equation, and then we got the answers is 196.8 and negative 192.6 km per hour. Okay, next we need find the corrected heading. Okay, for this theta prime equals to arctangent negative 192.9 divided by 169.8 and theta prime is equal arctangent negative 1.939 and the theta is approximately to equal to negative 48.1 degree. Okay, since it is in the fourth quadrant, we calculate 360 degree minus 48.1 degree equal to 311.9 degree. Okay, Captain Aiman must now navigate at the heading of 311.9 degree to maintain the specified course. His ground speed magnitude of the resultant vector is as follow. R modulus equal to 169.8 square plus negative 192.9 square, and we got this operation is 0.48 we got 66046.445, and we solve it and we got 259.9 km per hours. Okay, then the aircraft ground speed diminished to 256.9 km per hour as a result of the wind's influence. Okay, we go through to the next question. For this question, Captain Aiman has accurately determined his new course and ground speed to compensate for the intense crosswind. To maintain exact adherence to the plan, a more thorough analysis is required. Through the application of vectors mathematics, especially the dot product, cross product and scalar multiplication, Captain Aiman can fully understand the impact of wind on his flight and make more informed decisions. Okay, for the step 1, dot product, ensuring the correct heading. Okay, Captain Aiman wonders how closely does his adjusted heading 311.9 degree align with his original plan bearing 320 degree. To find out, he decides to compare the two velocity vectors using the dot product. He begins by representing vectors in component form. For the original velocity, A equal 300 in bracket cos 320 degree sin 320 degree. We using cos 320 degree equal to 0.766 and sin 320 degree equal to negative 0.643. Okay, next we sub the value. A equal 300 in bracket 0.766 and negative 0.643 equal in bracket 229.8 negative 192.9 km per hour. For his adjusted velocity, B equal 256.9 in bracket cos 311.9 degree sin 311.9 degree. We using cos 311.9 degree is equal 0.656 and sin 311.9 degree is equal to negative 0.755. B equal to 296.9 in bracket 0.659 and negative 0.755 equal in bracket 168.7 and negative 193.9 km per hour. Okay, next Captain Aiman applies the product formula. The formula is A multiplied by B equal in bracket 229.8 times 168.7 plus in bracket negative 192.9 times negative 193.9. Okay, next A multiplied by B equal 38747.9.26 plus 37394.31 equal 76141.57. Okay, to find the angle between the vectors, he used cos theta equal A times B over modulus A times modulus B. Okay, the magnitude of the vectors are modulus A equal punca cos square root of the 229.8 square plus negative 192.9 square, and we got 300, and modulus B equal to square root 168.7 square plus negative 193.9 square, and we got 256.9. Okay, next for cos theta is equal to 76141.57 divide by 300 times 256.9, and cos theta is equal to 76141.57 over 77070 equal to 0.98779, and theta equal to arc cos negative 0.6879, and we got the theta is 9.06 degree. Okay, Captain Aiman now realize his new heading divides by 9.006 degree from the original rod, a small but notable offset. Okay, next is cross product, understanding side drift. Okay, Captain Aiman then reflect on the wind's influence. He knows that even a slight lateral drift could push him off course, potentially leading to extra flight time or even a safety risk. To measure this drift, he used the cross product. Okay, A multiplied by B equal to modulus A times modulus B sin theta. Okay, A multiplied by B equal to 300 times 256.9 times sin 9.06 degree, and A multiplied by B equal to 77070 times 0.1574 equal 12136.552. Okay, this result 12136.52 represent the magnitude of the perpendicular drift, a clear indicator of how much the wind pushing him sideways. Captain Aiman now understands that even though his heading correction keeps him largely on track, the wind is still exerting a significant force and he must remain vigilant. Okay, for the lastly, the scalar multiplication increasing for the airspeed. Determined to make up for lost time, Captain Aiman considers increasing his airspeed by 15%. He calculates his new airspeed. Okay, first 300 times by 1.15 equal 345 km per hour. He converts this new speed into a velocity vectors. Vp prime equal 345 times by in bracket cos 320 degree sin 320 degree. Vp prime equal 345 times in bracket 0.766 and negative 0.643 equal in bracket 294.3 negative 221.8 km per hour. Okay, next he calculates the new resultant velocity factoring in the persistent westward wind of 60 km per hour. Okay, R prime, this is the formula. R prime equal Vp prime plus W. R prime equal in bracket 294.3 negative 221.8 plus in bracket 60 and 0 equal in bracket 324.3 and negative 221.8 km per hour. To determine his new ground speed, Captain Aiman calculates R prime in modulus equal square root 324.3 square plus negative 221.8 square, and when we calculate it, and we got 392.9 km per hour. Okay, finally he estimates the new flight time. Okay, for we know the time equal to 410 divided by 392.9, and we got 1.04 hours. or equal to 1 hours 2 minutes. By increasing his speed, Captain Aiman saved 22 minutes compared to his previous ground speed of 256.9 km per hour. Okay, from this scenario, we can draw several important lessons. With vector analysis, Captain Aiman managed to correct his heading accurately, minimize time loss, and improve fuel efficiency. This outcome shows how crucial vector mathematics is in navigation. On the other hand, if Captain Aiman ignored the wind and flew straight towards his original bearing without adjusting, several problems will arise. He would likely end up, of course, burn more fuel trying to fix the mistake later and risk passenger safety. This comparison highlights why vectors analysis is not just a mathematical concept, it is a practical tool that keeps flight and ships on track, saving time, fuel, and most importantly, lives. To conclude, vectors are an essential part of modern navigation. They allow us to make precise calculations, ensuring that planes, ships, and even space shuttles can maintain safety, efficiency, and accuracy during travel. By breaking force into components and calculating resultant vectors, navigators can counter environmental factors like wind and current. The example of Captain Aiman's flight to Langkawi demonstrates how mathematics, particularly vectors, translates from theory into practical, real-world problem solving. Without vector analysis, navigation would be a lot more challenging and far less reliable. Thank you for listening to my presentation, and I hope you now have a clear understanding of how vectors play a vital role in ensuring safe and efficient navigation.